For our next example, we're going to be taking a look at integer linear programming. Now, integer linear programming is very, very similar to regular linear programming, except integer linear programming will just constrict our variables to only being integers, which is the fancy math term for just being a whole number. So for example, if we were to think about the transportation example from before, we would not be able to produce half of a speaker, 75% of a speaker, a third of a speaker, because that wouldn't exactly be ideal for a consumer to play music through half of a speaker. Now, in terms of setting this up to use Solver, we're going to set this up the exact same way we have for our previous linear programming questions. Now I'm going to do sum product here because my objective equation is p equals 4x plus 5y. So here I'm going to highlight my coefficients first, the 4 and the 5, and then multiply that with my variables here. I hit enter, and again, should always get 0 for that. Now for my first constraint of 4x plus 2y is less than or equal to 55, I'm also going to use sum product. This is different than the transportation question because now I have coefficients in front of my variables, the 4x and the 2y. For transportation, remember it was just x1 plus x2 plus x3 and all the other situations there. So now I'll do sum product of my coefficients, comma, multiplied with my variables up there, hit F4, close, and I'll get 0. And we're going to work smarter and not harder here and just click and drag. Now I'm going to open up Solver, and what we're going to do first here is just set up this question as if it was just a normal, regular linear programming question. So my objective equation, our goal is to maximize this. So my objective is going to be my highlighted green cell. My variables be those highlighted yellow cells. There we go. Now for my constraints, I'm going to hit add, highlight the blue cells on the left-hand side, less than or equal to my right-hand side. And then I'm going to hit add. I'm not worried about integer programming or integer values for this right now. I just want to show you what this will look like as if we were setting this up normally. So now I'm going to hit run. And now my optimal solution is 11.875 and 3.75 to get an optimal solution of 66.25. Now, that would be great if we were allowed to get decimals. So for example, if we were dealing with the cost of something or wondering what the ideal cost would be for our variables, that would be okay. However, in this case, we're worried about our variables being whole numbers. Now, the natural instinct is to take 11.875 and let's just say we round that up to 12. Let's take 3.75 and round it up to 4. Awesome. We have whole numbers now. We have integers. Fantastic. Only problem is if we look down here in our blue cells, all right, this is saying when x is 12, if I were to plug it in, 4 times 12 plus 2 times 4, that would give me a total of 56. Which last time I checked, 56 is not less than or equal to 55, so that does not work for our constraints. Likewise, constraint 2, I would get 36, which is not less than or equal to 55. So if I were to have rounded that down to get 11, now this would work out, and I would get an objective equation of 64. Or my optimal solution would be 64. Both of my constraints work, but believe it or not, this is actually not our optimal solution. This is not maximizing our objective equation here. In order to do that, I would go back into the constraints. Or first, let me just delete my variables to reset it. Nothing has changed in Solver, so all I need to do is go in here. I can click on the left-hand side part, and I'll highlight my variables. And my variables are what I want to make integers. So I just now go into relation and I click on the integer button and I hit add. When I hit cancel, this is what you should have if you were just solving a regular integer programming question. You would add in your constraints of the left-hand side and right-hand side of your inequality, and then you could just add the additional constraint of making your variables be integers. So now when I hit run, Now when we added that additional constraint of making our variables be integers, the optimal solution is 10 and 5 for x and y respectively to give us an optimal solution of 65. And again, notice down here, when we do the sum product of our constraint coefficients with our variables, our left-hand side for our constraint 1 is 50, left-hand side for constraint 2 is 35, and that follows all of our rules that we have set in place. So that is how we can utilize integer linear programming using Solver. If you have any questions about this or any of the previous examples, please send me an email. If you need help with your project over break, let me know and I will get back to you as soon as possible. Thank you.